Welcome to 501 Math Lead, where we work smart, not hard. In today's video, we'll be looking at the Koch Snowflake. We'll be determining the area and the perimeter of this fractal. Let's begin with the area. So, how do we get the Koch Snowflake in the first place? We start off with an equilateral triangle, and then the side is divided into 3 equal pieces, and another triangle is added onto each side of dimension length equal to 1/3 of those lengths from the original triangle, and that step is repeated infinitely. So let's say we imagine that we have our first triangle of unit area. Then its area is divided into smaller triangles as we see there. That yellow triangle, its area, because its length is 1/3 of the side, is going to be 1/3 of 1/3, or in other words, the scale factor squared, so that is 1/9. And there are going to be 3 of them. So we have the area now being the original 1 plus 3 times 1/9. Then there's the orange triangle. That's going to be 1/3 of 1/3 in length squared, so it's going to be 1/9 squared, which is 1/81. And how many of those are there? Let's count. There's 12 of them. Then let's do it one more stage deep. We have the little red triangles. That's going to be 1/3 of 1/3 of 1/3, or 1/27th, but the area is going to be squared, so that's 1/729. And how many of them are there? Let's count, and we see that there are 48 of them. So when we look at this, we see that actually we have an infinite sum that can be somewhat simplified. Let's see, the 3 times 1/9 would be 3/9. The 12 times 1/81 is 12/81, and so on and so forth. Those can simplify to 1/3, 4/27, and 16/243. Then we can actually simplify that some more by saying the 1/3 is just 1/3, but the 4/27 is 1/3 times 4/9, and the 16/243 is 1/3 times 16/81. We notice that we have a common factor of 1/3 in each of them, but that 4/9 and that 16/81 is a power of 4/9. If we go further and we compare that to a plus ar plus ar squared, we can easily identify that a, our first term, is 1/3, and r, our common ratio, is 4/9, and we can use the formula to find the sum of an infinite geometric progression, s equals a over 1 minus r. Substituting our values, we'll have 1, the original area, plus 1/3 divided by 1 minus 4/9. 1 minus 4/9 is 5/9. 1/3 divided by 5/9 is the same as saying 1/3 times 9/5. The 3 and the 9 cancel, and we get 1 plus 3/5, or in other words, the area is 1 3/5. And next, let's look at the perimeter. So with our shape here, let's break it down into stages once again. We have our initial stage, or our 0th stage. In our initial stage, let's assume that the perimeter is 1. Then when we look at our stage 1, we'll see that that side there that is in green, that actually is the same as this side here that is outlined with the blue arrow. So in actuality, it's only one new little side that is added on there that we see in green. So that is 1/3 of them. And since there are 3 sides, it's actually 3 of those that are added on, 3 1/3s. Then in stage 2, each of those would be 1/3 of the 1/3, so they're in length 1/9. And if we were to count all of them around, we would see that there are actually 12 of them. So it's 12 of those 1/9, 12 of the sides. In stage 3, those would be 1/3 of 1/3 of 1/3, or in other words, 1/27, and there would actually be 48 of them. So once we do our calculations, we see that once again we have a geometric infinite series, and we can simplify. The 3 times 1/3 is 3/3, 12 times 9 is 12/9, and so on and so forth. Reducing, we'll get 1, 4/3, and 16/9, etc. So that 4/3, we can actually say it's 1 times 4/3. The 16 over 9 is actually 1 times 16 over 9. And then even furthermore, that 4/3 and that 16 over 9, we can say that 16 over 9 is just the square of 4/3. So we have indeed confirmed that it is a geometric infinite series, where if we identify our A and our R, A, the first term in this case, would be 1, and R would be the 4/3. Substituting into our formula, oh wait, nope, we can't, because this formula only converges if the geometric ratio R is a number less than 1 or greater than -1, or in other words, if the absolute value is less than 1. But since this common ratio R is bigger than 1, then that means this sum blows up to infinity. So we come to the astonishing fact that for the Koch snowflake, it has a finite area which is only 1 3/5 greater than the original triangle, but its perimeter is infinite. Isn't that amazing? I think so. Do you do too? Well, as always, if you found this video useful or you enjoyed it, please hit that like button, share with others, and subscribe if you're new here.